This is a note about the cavitation constraint in the project, so just to try to better understand the relationship with the critical pressure coefficient and what we're trying to do with X-foil in terms of determining the max CL that we can get without violating the critical pressure constraint. So this pertains actually to what we talked about in class and the last question on the midterm, this idea that you have a free surface. You have some hydrofoil operating under the free surface. And what we're basically asking ourselves, at what point do we reach a pressure on the foil P that's less than the vapor pressure? And that's the point at which we'll have cavitation. So we have very far upstream of the foil, we have this parcel of fluid. It's a depth h below the water column. And the free stream pressure, P infinity, is equal to rho GH plus P atmospheric. And this parcel of fluid is going to come and it's going to accelerate over the body of the hydrofoil. And at some point we do know here that the pressure will be less than free stream. The question is, how much less than free stream? Is it far enough less than free stream that it's going to reach the vapor pressure? We can ask that in terms of the pressure coefficient, Cp, defined as P minus P infinity divided by the dynamic pressure. And we can write this as a critical pressure coefficient. So this P right here is the pressure anywhere in the fluid, and we don't want that falling below the vapor pressure. So we can define a critical pressure coefficient. I think we called it CPC. I forget what I called it in the assignment. We'll just call it that for now. Equals the vapor pressure of the fluid minus P infinity over 1/2 rho U infinity squared. And we can say if CPC is below, if the minimum pressure anywhere on the foil falls below this critical pressure coefficient, then we can say we're having cavitation. We're likely having cavitation. And so when we look at this critical pressure coefficient here, the denominator is fixed for the problem because the speed is fixed and the density of the fluid is fixed. The vapor pressure is fixed because that's a property of the fluid, and that leaves you with this P infinity is a function of the depth. So at greater depth you have a larger or higher free stream pressure. The implications of that in general we can think about in terms of, let me just note that, so you're considering the hydrofoil different depths, so you have to compute different P infinities or actually really different critical pressure coefficients. If we think about this in terms of a foil, we have a foil that looks like this. I'm going to run out of room, sorry. If we think about a typical pressure distribution on a foil, we have a cambered foil looks something like this. And if we draw our pressure distribution on top of that, so that this is Cp equals 1, we'll do our usual inverted business, equals 0, minus 1, and minus 2, and I'll just draw on the upper surface pressure distribution. Let's just say it looks something like this. And that went pretty high. I'm not going to put it quite that high, sorry. Let's just say it was something like this. So we can see that the lowest pressure achieved anywhere on this foil is, typically somewhere towards the leading edge on the upper surface. And here I'm seeing a value of something like minus 1.5, something like that. Now this critical pressure coefficient, again, depends on the speed of the foil and the depth of the foil and the vapor pressure. And so that's just a number. That's just a number. And so let's say it ends up, for the conditions that the foil is traveling at, let's say it ends up being somewhere around minus 1. So let's say it's about minus 1. And I think this minus 1, if I remember correctly for the project, I think you get a value about minus 1 for a depth of 5 meters, if I remember correctly, but don't quote me on that. So minus 1. Now, if we were to decrease the speed of the foil, and you go back to your critical pressure coefficient, what it would do, so actually let me effect. So this particular foil in this lift condition would be cavitating under those conditions. Now, if we were to slow down, what would happen is that the line would go in this direction, that our critical pressure coefficient would become more negative, and that dash line would move up, and we would no longer be cavitating if we were to slow down. If we were to speed up, so this is slow down, speed up, it goes in the other direction. Slow down or deeper does the same thing. This would be a deeper hydrofoil. Both of those would move the line in that direction and take this cavitating hydrofoil and make it not cavitating. And we can think of the vice versa situation. Now, in your case, for a particular depth, your speed is fixed, so the only thing that's controlling the critical pressure coefficient is the depth. If we're thinking about a particular depth and we're trying to figure out the maximum lift we can achieve on a given foil at that depth, then that purple line is effectively fixed. And then what we're doing is playing with the lift coefficient. So if I were to come back in, and this red line that I drew, the pressure distribution is for some lift coefficient. If I were to reduce that lift coefficient, typically when you reduce the lift coefficient, it's reducing that suction peak. So it might look something more like this. So this is what would happen if you were to lower the lift coefficient, lower CL. So if you were to lower CL, you could also produce, reduce the chances of cavitation. And effectively what the exercise is to do is to figure out the highest CL you can achieve before you cross that purple line. You're looking for that max kind of CL. Because what happens is, because lift is equal to CL times 1/2 rho U infinity squared times S, and this business in here is fixed. So basically you have lift is basically proportional to CL times S, and lift is fixed. So basically CL times S is some kind of constant. And so if you are reducing CL or forced to reduce CL, then you are forced to increase S, which generally means a lot more friction is going on. And so commensurate with this is this sort of idea of what happens when you use thicker foils. And so think about a very thin foil can produce a lift, a low level of lift coefficient without too much suction peak, because the fluid doesn't really have to accelerate too much to get around the edges. Once you start using very thick foils, which is what happens when you have a large span, if you have a very thick foil like this, even at low lift coefficients, the fluid still has to accelerate to get around this thing, which means you're getting, even at low lift coefficients, you get quite negative pressures, and you're more likely to cavitate, meaning you have to go to pretty low CLs to avoid cavitation if you have a thick foil. So a wider span, so if you make B go up, your span go up, that's usually good for lowering your induced drag. However, generally speaking, you might find that CL is coming down, which means S is going up, which means you might end up with some more friction drag, which might be offsetting the advantage of the lowered induced drag. You can kind of see how those are trading off a little bit. So anyway, so that gets to this idea of the trade-offs of the different components. Now, in terms of X-foil, I will attempt to bring that up. I don't know if this is going to work. All right, so if I run a case here, and what I'll do, let's just start with talking about just one foil. So I'll use the example that I put in my course's list of commands. So that was a 25015. So for your project, this would be a 15-meter span hydrofoil. And let's say it's at that 5-meter depth. So we're thinking about critical pressure coefficient about -1. And again, don't quote me. I can't remember if that's right or wrong. But I'm going to say -1. And I'm going to set my operating conditions, and I noted a Reynolds of 30 million. And what we're going to do is I'm just going to do a CL of 0. Let's see what that looks like, and see if I'm in my, I plotted on my other screen, so give me a second. Okay, so this is what it looks like. This is what it looks like. So we have actually the minimum pressure is being reached on the lower surface. You see the red here? The fluid's actually coming in and it's accelerating more to get underneath than it is to actually get up and over. And that's not surprising for a cambered foil, a thick cambered foil at a low angle of it, at a low lift coefficient. The angle of attack is sort of irrelevant. We're thinking about lift. That's the most important thing. So we would not be cavitating at this point because the minimum pressure coefficient is below this line here. In fact, I think I can get it to print what it is. Cp min. It is the viscous solution minus 0.91. So it's below, in this sense, it's less negative than -1. So the actual peak is somewhere around here. So we're calling this -1. Pretend there's a line extending from -1 straight across. And we're trying not to cross that line. So we say, okay, well, with zero lift, we're okay. How about a lift coefficient of 0.1? Let's see where we are here. Okay, things are actually improving, and we'll see why that is when I go back to the chart. CL of 0.1 with some lift, we're at about I can find out what it is exactly. Cp min minus 0.7 is what this is, and actually looks like the upper surface is now the limiting factor here. And if I go to CL of 0.2, I'll just check a Cp min while I'm here. Minus 0.8, we're up to now. We're still okay, we're not cavitating. I can go to CL. Oh, I forgot what CL I just did. Is it 0.2? Sorry, it's getting late. Okay, so CL of 0.25, minus 0.85. Let me go to CL 0.3. Okay, so now we're getting close. Minus 0.93, we're getting close. You can see the suction peak right here, about quarter chord or 20% of the chord, somewhere around there. Definitely upper surface, blue line. And we're getting close to -1. And if I go to CL of 0.35, I suspect we will have crossed, no, we're right on the line. So I don't think we can go much more than 0.35. And we're going to hit, so you can see the CL here, we're going to hit this barrier. Now, at this hydrofoil, we're operating at a lesser depth. We'll say the critical pressure coefficient were let's just say minus 0.8, something like that. You could see we'd already be cavitating. We would have had to pick a lower CL before we cavitate. So in this case, we're thinking about where does it cross a given line. We were talking about -1 here. So rather than sitting here and iterating, what I advise you to do is just run a range of angles of attack at pretty discrete levels in order to get at this. And so to do that, you I advise doing iter 400, and what this does is when Xfoil is running, it actually runs this iterative solver where it solves for the inviscid pressure distribution over the foil. Then it computes the boundary layer properties by integrating from the leading edge back. And that adds what's an effective thickness or displacement thickness to the foil. So the flow that comes in sees a kind of a thicker foil because of the boundary layer. And then it redoes the pressure distribution for that slightly thickened foil, which then changes the solution. Then it goes back and runs a new boundary layer. And then, so it has a slightly boundary layer, and so it goes back and forth between these two solvers and hopefully reaches in a state where both of them agree, the inviscid and viscous distributions agree. And that's what this iter does. That tells it the maximum number of iterations to do. The original flow solver for Xfoil was built when computers were quite not what they are today, and so they kept the default at a small number. And you can use a much larger number and it doesn't affect your compute time by today's standards. So then I'm going to save everything in a polar file, including min.cp, which was what sync does. I'm going to accumulate my polar file. I'm going to call it 25015. That's the name of the file. I don't need to do the dump file for this. And then I'm going to run a sequence of angles of attack from -3, and honestly for the project we probably could have started at 0. I'm not sure why I did that, but to 8 degrees at angles, increments of 0.1. So it's going to blast through these. You can kind of see it's throwing all the pressure distributions in here. We're going way up there. Obviously, we're way over anything in the project at minus 2.5. I don't know when it crossed there. I can't really see it from here, but so that's done. And what this will do is, if I control D out of here and open this up in DI, I can see this listing here. So basically this shows is what's called an airfoil polar. So it shows for each angle of attack, the lift that's achieved. Now at minus 3 degrees, it achieves a minus lift. It's actually lifting down. The drag coefficient due to pressure. So this is the viscous pressure component. This is the total drag coefficient. This is the moment coefficient. This is the minimum pressure that's achieved. This is, and these are the transition locations. So where the boundary layer is transitioning in percentage, in fraction of chord, 33% on the top, 4% on the bottom. And these are actually the airfoil is broken down into panels. So these are the panel locations where the transition's occurring. And then you can go down through the angles of attack, and you can see what happens. We'll just see we'll see the table here, and I'll try to pull this into MATLAB and plot it, if I can do that. So if I'm looking, we only really care about positive CLs because we're trying to lift something up. So starting here, we can see that at low CLs, we have a minimum pressure coefficient of about minus 0.75. It actually drops down a little bit as you go to higher CLs, down to minus 0.8 of CL. We're getting minus 0.7 for minimum pressure coefficient, and now it's coming back up. So if our pressure coefficient, if our minimum pressure coefficient was minus 1, let's say it happened to be minus 1, I haven't hit it yet. If my cursor's on the column for the minimum pressure coefficient, I haven't hit it yet. I just hit it. So the last CL at a minimum pressure coefficient before we went below that minus 1 was 0.37 for this particular foil. I'm not sure what you're running in the project, but for this particular foil, if I were to take this foil and move it to 0.38, a lift coefficient 0.38, then my minimum pressure is now minus 1, and so we have cavitation. So graphically speaking, I will attempt to pull this in MATLAB, but if I fail, I apologize. So let's see if I can get this in. So I'm going to read this into MATLAB. Okay. And I'm going to plot, what am I going to plot here? CL versus CDP, CP min. Okay, so what I'm plotting here, CP min is from the polar data. I'm plotting, make sure this is getting recorded. This is the lift coefficient. So this comes from the table I was showing you. I read in all the columns, but I'm only plotting the CL column, which was column 2, versus the CP min column, which is 1, 2, 3, 4, 5, 6, column 6. So you can see here, here's CL 0, and obviously we don't really care what's going on here. So imagine again a line here. So this is with CP is positive up. So here's your line minus 1. We don't want to fall below that line. We don't want to be more negative than that line. And again, it's a little confusing because in our polar plots we were just looking at for the foil, remember the CP is upside down. So the key is not, if you're more negative than your critical pressure coefficient, then that means your pressure is lower than vapor pressure and you have cavitation. So I want to stay above this minus 1, or be less negative than this minus 1. And so I'm thinking about positive CL. So I want the maximum CL I can get looking for the maximum CL I can get before I cross that line. I don't have the line plotted on here. I could do it, but anyway, it's not bothered. So So I'm falling, and some are minus zero point 0.3, whatever it was, I forget now, 3 something. Yeah, I'm right here, so I can see y is minus 0.96, right around here, 0.35. I cross that line, and if I push the CL any higher, then we are more negative than minus 1, and it's cavitating. So this is basically that same conversation I just had, plotting the polars one by one in X-foil, increasing CL. We were pushing that suction peak up. That's the same as dropping down this minimum pressure and making it more and more negative. It's the same as pushing the suction peak up. So I want to figure out where this crosses. Um, and that's essentially the exercise you're doing. But you can do that with an algorithm in MATLAB if you want to do it. You can do it by just simply opening up the table, as I've done here, and eyeballing it. And again, I'm just scanning down. I want positive CLs. I'm scanning that CP min column. I'm seeing it getting worse, 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 until I hit minus 1 right there. So that would be the CL max that I would record for this case, 3747. Obviously, for all your cases, it will be different than that.